diffracted. So what you see is the central maxima, first order minima, first order maxima, and so on. Now, if we have a convex lens in between, then the lens collects the diffracted light and focuses it on a screen. This results in the formation of the image of the slit. So the image is nothing but an interference pattern of the diffracted light. Now, a very important point to note over here is that it's the edge of the slit that diffracts the light. So to see the edge of the slit clearly as an image, the lens must collect the diffraction pattern. If the lens fails to collect the diffraction pattern, the image formed is blurred. Now, as the width of the slit decreases, the diffraction increases. Soon there comes a point where the objective fails to collect the diffraction pattern. When this occurs, the image formed is blurred. A similar phenomenon occurs when we try to see the small specimen with a microscope. As the specimen size decreases, the image gets blurred. The resolving limit of light microscope is given by Abbe's equation, and according to this value is roughly 200 to 250 nanometers depending on the wavelength of light used. The red light suffers maximum diffraction because of large wavelength, and hence resolution obtained is low, while the blue light suffers less diffraction because of short wavelength, and hence resolution obtained is high. So the idea is, if we have less wavelength, the diffraction will be less and resolution will be high. In the year 1924, French scientist Louis de Broglie gave a beautiful concept of matter-wave equation. According to this, moving matter can have a wave nature associated with it. This was experimentally proven in the year 1927 using electron beam as a source of particles, and they did behave as waves and formed a diffraction pattern just like photons did. Now, because the mass of electron is much more than the mass of photon, the wavelength of electron beam will be much less than the ordinary light of photons. Ernest Ruska realized this in the year 1933 and invented the first electron microscope. When the electron beam behaving as a wave hits the tiny specimen, it does suffer diffraction. However, the diffraction is less as compared to light of photons. Now, as the diffraction is less, this can be easily collected by magnetic lenses to give rise to clear, sharp image of the specimen. Let's see the construction of transmission electron microscope. The transmission electron microscope has an electron gun as a source of electrons. As the moving electrons have magnetic field, they can be easily focused using electromagnetic lenses. Now, just like an optical microscope, TEM has a condenser lens, objective lens, and a projector lens. However, these are all electromagnetic lenses. Electrons are focused on the specimen using the condenser. The diffracted electrons by the specimen are collected by the objective lens. The electrons from the objective lens moves through the projector lens, which projects the image of the specimen on the fluorescent screen. In transmission electron microscopy, the samples are usually stained with uranyl acetate. Now, let's talk about scanning electron microscope. As the name suggests, this microscope scans the specimen and gives high-resolution images of the surface. The SEM consists of an electron gun as a source of electrons, condenser lens, an objective lens which focuses the beam of electrons on the specimen. The scanning coil usually scans the electron beam in X and Y direction. The specimen is coated with heavy metals like gold, platinum, iridium, chromium, and tungsten. The presence of these heavy metals on the surface allows the electrons to be scattered. The scattered electrons are detected by electron detector, and finally information about the surface of the specimen is obtained on the computer. Now let's talk about cryo-electron microscope. X-ray diffraction have been one of the long-term dominant methods to obtain information regarding crystal structure of protein. In this method, X-rays are allowed to pass through crystallized protein and the diffraction pattern is obtained. Using the information in the diffraction pattern, the location of each atom is deduced to obtain the protein structure. However, the major drawbacks of X-ray crystallography is that proteins need to be crystallized, and crystallization of proteins is very difficult. Because of these drawbacks, people started searching alternative methods to obtain 3D structure of proteins. This was cryo-electron microscopy. In this method, a beam of electrons is fired at a frozen protein solution. As the electrons get scattered and diffracted, they pass through electromagnetic lenses, which creates magnified image on the detector. An interesting thing to note over here is that the frozen protein solution can have protein molecules in different orientation. Hence, while taking multiple images of protein molecules in different orientation, a 3D image of protein can be obtained by combining all images using a software.
Hola, hola.
Hola, profe.
¿Sí me escuchan?
Sí, sí.
Sí, profesor.
Pues yo espero que esto haya sido como no muy largo y claro, pues les haya hecho ver las partes de los microscopios de transmisión, perdón, de electrónicos en detalle. Mi intención es, pues, que ustedes las conozcan, ¿no? Yo sí les pediría un resumen de todos los videos con el fin de que pues estemos claros en todo lo que son los componentes, la forma en que trabajan, ¿verdad? Y normalmente les pido que ustedes de tarea busquen más, ¿no? Diferentes de partes de microscopios, como los vimos hoy, ¿no? Esquemáticos. ¿Qué les parece?
Sí.
Un resumen de videos sobre componentes del microscopio electrónico. Y los tipos de microscopios electrónicos, ¿verdad?
Profesor,
Perdón, diga usted.
¿incluimos el crío?
El crío, yo creo que nada más en el resumen particular del video no lo vamos a estar viendo, ¿verdad?
Ok.
No es parte del curso. Uh-huh. Conceptos importantes que se han manejado. como la resolución espacial, ¿verdad? ¿Cuáles son las ventajas sobre microscopios ópticos? Y esas ventajas, ¿sobre qué están fundamentadas? ¿Cuáles son las razones? Yo opino que ya todo eso se vio y que está en los videos. Si alguno de ustedes tiene dudas, pues ahorita es cuando hay que preguntar, ¿ya? O los volvemos a repasar. ¿Cómo?
Creo que está claro.
Hello friends, in this video
Hay algunos de estos que no es en mi lista. Videos. Pero pues, hay tantos que es difícil, ¿verdad? Entonces estoy anotando una vez todos estos.
we'll be talking
Entonces,
about S.
¿alguna duda, alguna pregunta?
Una pequeña duda, pero no es sobre los microscopios, sí es igual sobre lo que nos dijo el sputtering, es una duda pequeña.
Ujú. ¿Quieres preguntarle ahora?
Sí, se puede, sí. Nos dijo que, bueno, por lo que he entendido, pues el sputtering es básicamente una erosión por el contacto de una superficie con el plasma. Nos estaba diciendo la otra vez, pues que el blanco se pone en pues en una especie como de cono helicoidal. Entonces, la pregunta que tenía es si, bueno, es que vi que hay dos tipos de manera de hacer eso, que se produzca el plasma en el mismo material y ese plasma pues vaporiza el material y se ha depositado, o que se bombardee con plasma el material, ¿no? Entonces, pues nada más quería saber en el caso del crecimiento que se hizo, ¿cuál de las dos fue aplicada?
En el caso que hicimos nosotros es el que le pones un pedacito de lo que vas a, de lo que quieres encima. ¿Sí? El que yo estaba explicando. Si quieres oro, le pones un pedacito, ¿verdad? También
Entonces,
hay filamentos de oro, ¿verdad? Y el sputtering se hace directamente, ¿no? La desventaja de estos es de que siempre depositas oro, ¿no? Entonces, si tienes el electrodo de otro material que es más resistente al sputtering, primero va a llegarse al límite de otros materiales, ¿no? El tungsteno es usual que resiste mucho y se evapora, pero no tanto. Y por eso es que yo preferí comprar uno así, ¿no? Por si quieres poner oro o lo que sea, ¿no? Me estoy atorando porque creo que en esta presentación que les mostré hablaban directamente de eso, ¿no? Dejen ver. Que se recubrían las muestras con diferentes cosas, ¿no? En uno de los videos se hablaba de eso mucho. No lo encuentro así rápido. Ah, no, aquí nada más se describe. No. Pero lo vamos a estar viendo porque mi intención es seguir con un par de videos, pero ya de operación, ¿no? El que tenemos nosotros, entonces se coloca un pedacito y se evapora. ¿Sí?
Pero entonces o sea, las partículas que forman el plasma que evapora el blanco son pues electrones emitidos por el tungsteno.
No. Sí, o el calentamiento que se hace es a través de este arco eléctrico. Creo que estamos hablando de quizás de cosas distintas. Tú estás imaginando que sale un electrón o un átomo del blanco, ¿no? ¿O cómo estás imaginando el sputtering?
Ah, bueno, por lo que leí, pues más bien se bombardea el blanco pues, con partículas de alta energía en forma de plasma.
Ese es uno un poco más caro. El otro es que se hace un arco eléctrico. Mira aquí por ejemplo. Creo que aquí está esto. Les voy a compartir esta pantalla. Lo que tenemos es estos dos electrones y aquí en medio va lo que se va a depositar, ¿no? ¿Sí todos ven la nueva pantalla?
Sí.
Ah, ya está compartir sonido. Entonces la paso para que lo vean.
Hey everyone, I was finally successful in depositing a clear conductive layer onto a microscope slide. So this will be the basis for a lot of my future experiments in OLEDs and other display technologies. So let me show you how I did it. The device that's actually doing the depositing is called a sputter gun, and I machined mine from basic pieces of metal, and I'm going to unscrew it here like this, and eventually the whole thing just comes off like so. And down in the hole here is a spark plug, and it's facing up towards us. So on the underside, there's the rest of the spark plug, of course, and then right next to it there's a needle valve with a hose coming off, and the hose runs to my argon cylinder. So I can control how much argon is getting into the chamber through the needle valve, and I can get high voltage into the chamber through the spark plug. And the underside of the
¿Sí
sputter
escuchan
gun.
todo?
Perdón, ¿qué
Hola,
dijo?
hola. ¿Sí escuchan todos el video?
Ah, sí.
No es exactamente el que tenemos nosotros. Ese es, yo creo que mucho más caro, pero
Sí,
parecido, ¿no?
profe.
Bueno. Hola, hola. ¿Me escuchan? Porque alguien quería decir algo y parece que lo interrumpí.
Sí, lo escuchamos.
Sí, que sí me escuchan y que sí escuchan el video.
Sí.
And has a rod in here that contacts the top of the spark plug. So I have sort of a shielded entry into the chamber. The sputter gun itself is relatively simple in construction. So let me just take it apart and show what's inside and then describe how the whole process works. So the very outside is called a ground shield, and it slides off like this. And the purpose of this is just to keep the things that you don't want to sputter inside this. So when the shield is on, the only thing that's exposed to the chamber is the surface of this disc here, which is the thing that we want to sputter, to send off onto the microscope slide. So if we take that off, the rest of it is built like this, and between these two layers is an insulator. So we'll take this apart, and currently there's some changes that I'm going to make to this. These are nylon screws and nuts holding it all together, and nylon is not really a great vacuum chamber material. So eventually I'm going to upgrade this, but I'm not quite sure what I'm going to use instead. And so this part is at the vacuum chamber case potential, let's just call that ground. And then the inner part here, this is where it touches the spark plug. This is all at a negative high voltage, let's say 1000 volts negative. So inside here, we've got a very high potential between this outer shell and the inner shell, but there's a few other tricks here that allow us to sputter just the target material and not sputter the rest of it. So I'll open this up, and as you can see, I'm missing quite a few screws because I haven't got the right ones in yet, and I just wanted to test this quickly. Inside here is a magnet, a ring magnet, neodymium ring magnet, and a steel pole piece that I turned on the lathe. And so the idea here is that when the magnet is inserted into here like this, there's a nice magnetic field on the top here. And you can even see one that I cracked my disc, unfortunately, so I'm not going to undo the top layer just yet. But also that there's a ring pattern where the disc has been eroded by the sputtering. I've also got some holes in here for a cooling system, which unfortunately I didn't have running yet, so that's hence the cracked disc. And the idea with that would be, this is a sort of a Teflon hose. It's actually called a plastic called PFA. With an O-ring on like this, the hose can be sealed up to this, and then with an O-ring in the right spot here, this whole thing closes up and I can actually pump water through the copper block. So a lot of sputtering systems say they require water cooling, and I always thought that only applied to like systems that ran for 8 hours a day. I figured that the thermal mass of this block would be enough to keep me safe for a 5-minute run. But as it turns out, not quite. I'm not sure if this was due to my clamping or too much power or something, but I think water cooling is kind of a necessary thing if you want to sputter stuff at any reasonable rate. Okay, so let me tell you how this thing actually works. So if you want to make a nice uniform coating on something, say like a microscope slide, you have a few different options, and two of the most common ones are evaporation and sputtering. So in a previous video I described the evaporation process, and this entails heating up the material that you want to coat. Heating up the material with which you want to make the coating, and typically that's done in a metal boat like this. So what we do is pass a really high current through here. This thing becomes very, very hot, white hot even, yellow hot, and the material here evaporates and then condenses on the thing that you want to coat. So this is, roughly analogous to boiling water in the kitchen and then noticing water droplets condense on a cold window. The downside with this is that you have to heat up the material to that yellow hot temperature. So if your material can't take it for whatever reason, or if it changes into another material at that temperature, then this isn't going to work. And when we're talking about making conductive ITO coatings, this is definitely the case, where if you heat ITO up in a vacuum, as far as I know, it reduces itself back down to base metals, and it doesn't work. So an alternative process is called sputtering. And this works by accelerating gas molecules and slamming the gas molecules at very high speed into the surface of the material with which we want to make the coating. And when that happens at just the right energy levels, it actually chips off a few molecules of the surface, off the surface of this material, and they go spraying off into the chamber. And eventually they'll land on the thing that you want to coat. So here's a cross-section view of the sputter gun. The ITO disc is the thing with which we want to make the coating. And then we've got our magnetic pole piece here with north and south poles. It doesn't matter which is which, I don't think. The idea with the pole piece being that the magnetic flux goes through the steel and then back up, through here. So the magnetic field lines look like this. This whole intersection here is at about negative 1,000 volts, and the outer section is at 0. So when we pump down the chamber to a very low pressure and put our 1,000-volt potential difference on here, the remaining gas molecules in the chamber will ionize, basically just like they do in a neon sign. And the trick with the magnet is that it concentrates all of the electrons in this area. And it does this because the electrons are relatively lightweight and they have charge. So the moving electrons are affected by these magnetic field lines. In fact, they actually spiral around the magnetic field lines. So we've concentrated all the electrons in this area. However, it's not the electrons that are actually doing the sputtering for us. What happens is these spiraling, fast-moving electrons end up ionizing more gas molecules. And it's actually the gas molecules that are attracted to this negative potential and hit the surface and cause the sputtering to happen, which is why this is negative and the shield is relatively positive, or at 0. This negative voltage attracts those positive gas molecule ions, and that's what causes the sputtering. The reason that we use argon is because we don't want an incoming gas molecule to react chemically with our material here. So for example, let's just say we were sputtering aluminum and we had oxygen up here. What might happen is a really energetic oxygen molecule might hit this and create aluminum oxide. It might not actually sputter the material, it might react with it. And sometimes that's desirable depending what kind of process we're doing, but generally you'd want to control those gases very carefully. So for a lot of sputtering, we just use pure argon. The exact pressure at which this whole process works is very critical to determining the success of your coating. So if you have no gas molecules up here, obviously the process doesn't work at all because there's nothing to cause the sputtering. That's at a really, really high vacuum. At really, really poor vacuums, if you have tons and tons of gas molecules up here, it's true you'll certainly be able to slam them into the surface. However, the high pressure is such a good conductor because there's so many ions, it's tough to get the voltage high enough so that the incoming ions are going too slow to cause the sputtering to happen. You'll have a nice glow discharge and things will look like they're working, but you just can't get the voltage high enough without, blowing everything up basically. Another problem is that if you have tons of gas molecules up here, when you eventually do sputter off a piece of the material, it's going to interact or it's going to hit those gas molecules. And that may or may not be a good thing depending how your setup is configured. So if your surface to coat is kind of up here, you generally want these sputtered molecules to have a fairly clear path toward it. If there's so many gas molecules up here that a lot of the sputtered material interacts with the gas and kind of starts flowing, that may be a bad thing because they're going to escape and coat other things on the surface of your chamber. It seems in the literature that most people prefer 10 to 100 millitorr for proper sputtering pressures, but it's also very common to use the diffusion pump anyway and pump the chamber way down as low as you can get it basically, just to clean everything, to get the water molecules and everything to evaporate off the surface, and then backfill it with argon back up to the pressure that you want. In my first few experiments here, I've noticed that controlling the pressure is actually surprisingly difficult and also, as the literature says, has a pretty profound effect on how the sputter process is going. I've been using an electrophoresis power supply for my first attempts here, and it turns out to be a very non-ideal power supply for this purpose. Besides all the stupid safety interlocks that make it difficult to use, the supply goes into its current limit condition kind of too quickly, and it's hard to get a consistent voltage current out of it. It is nice that it has a constant power function, so you can actually set a desired wattage and then play with the chamber pressure, and it will balance the voltage and current without exceeding that power limit. However, I think for future experiments, what I'm going to use is just a microwave oven transformer with the standard diode and control it with a variac. I've also been working with photoresist and making patterns with it using some UV lamps. So this will be coming up in a future video. Okay, see you next time. Bye.
Hola, hola, ¿me escuchan?
Sí,
Sí, profe.
Pues este video se concentró mucho en el equipamiento, ¿verdad? ¿Quién preguntaba? Creo que Axel o
yo, Samuel.
Samuel. Se ve un poco, ¿verdad? Del proceso, pero en principio no es un plasma que golpea algo, es como un arco que hace que los iones o los átomos se depositen, ¿no? Como, pues, poco, pero en el espíritu del video se encontraba, ¿no? Yo normalmente preparo la clase y veo los videos antes de mostrárselos porque muchas veces pasa esto, ¿no? Los videos tienen a veces errores. ¿Alguien iba a decir algo?
Sí, bueno, sí entiendo eso, pero bueno, aún así fue de bastante ayuda el video. Aún así, pues en el video menciona que usa argón precisamente para crear ese arco por encima del material que se quiere evaporar, ¿no? Igual en el caso del oro y los nanotubos.
El mismo procedimiento, ¿no? Se deja una cantidad muy pequeñita de argón después de hacer vacío para, pues, quitar primero todos los oxígenos y todos los nitrógenos que puedan interferir, ¿no? O la mayor parte de ellos. Después se sigue el procedimiento de inyectar un poquito de argón y hacer el arco, ¿no? Que es precisamente la aplicación de un voltaje y de una corriente.
¿Usó argón?
¿Podríamos quedar que para la clase próxima buscamos mejores videos de esto? Tanto ustedes como yo. De manera que quede completo y a satisfacción de todos.
Ok,
Les
muchas
digo
gracias.
que
Sí, profesor.
todos busquemos porque, pues, es tiempo que invertimos y tiempo en el que aprendemos y tiempo en el que vemos cosas, ¿ya? No es por otra situación, sino con el afán de, pues, que el tiempo que estamos dando de clases en línea les sirva a ustedes, que es a los que tiene que servirles, ¿no?
Me parece,
En-
claro, me parece muy bien, pero creo que también mis compañeros y yo, pues tenemos duda un poco con el reporte, porque el reporte de síntesis de nanoalambres, bueno, la fecha de...
bueno, la podemos posponer para el martes que sigue o el jueves que viene y mientras hacemos esto, ¿no?
la entrega era hoy.
Ok, profesor.
Estaría muy...
Nada más que la fecha límite de entrega de reportes, y lo tienen que tener claro, es el 20 de diciembre, ¿no? No podemos ir más para allá. Así es que mientras trabajamos en eso, trabajamos en los otros, en los que estamos ahorita haciendo, ¿verdad? Por eso les pedía que hicieran resúmenes para que en el reporte pudieran ya meter resúmenes
Profe.
o una versión de los resúmenes. Diga usted, Albertano. Nada más dijiste ok o querías hablar, Albertano. Hola, hola. Bueno, pues parece que no fue Abretano o no me oye.
Sí, fui yo, es que es como que tengo mala conexión y se corta. ¿Habrá alguna bibliografía que podamos consultar? Bueno, yo encontré algunas, pero tienen como muy vago la explicación, como que se enfocan en ciertos temas muy específicos. Bueno, es lo que he estado viendo ahorita que ella está investigando sobre los temas, es que ya no hay como algo que nos oriente, sino son muy específicas los procesos, si van a
Claro,
trabajar algo.
los
¿No habrá
procesos
alguna
son
que nos ayude
específicos.
para este tema o estos temas?
No hay un resumen, por eso es que yo hago las presentaciones resumiendo y poniendo todos los detalles, ¿ya? En microscopía por eso le estaba pasando las presentaciones y venir a clase y tomar notas y preguntar, ¿verdad? Pero un lugar donde haya una síntesis de microscopía electrónica pues, no existe, ¿verdad? Un libro tampoco. Un libro de difracción de rayos X con una síntesis no hay, ¿verdad? A lo mejor la Wikipedia tiene algo así, ¿verdad? Pero por eso es que a mí me parece interesante el laboratorio para darles a conocer los métodos, cómo se usan y por eso están las presentaciones que yo produzco. Y pues venir a la clase y tomar notas, ¿no? ¿Me explico?
Yo encontré, sí, yo encontré bibliografía de Sputnik, pero igual como usted dice, pues no es una síntesis, ¿verdad? Es un
Son
librote ahí.
gente que se dedica a eso, ¿verdad? Pero no por eso no podemos aprender un poco de eso. Me apura un
Un
poco
poco.
que nos queda menos de un minuto. Si hay más preguntas,